Good afternoon, students. Welcome to Analytics Powered Virtual Interactive Classes. So, how are you all? Hope all of you are doing great. Very good. So, in our previous class, yesterday, we were talking about how whenever a conductor like a electrical wire carries electricity, what produces? One kind of magnetic effect, right? And last, what we saw at the last, we saw that whenever we surfaced the electrical wire with the iron nail and we connected that wire with the battery or electrical cell, what did it showed? It attracted the iron paper clips, isn't it? Like whenever we created the circuit by preparing or connecting the electrical wire with the batteries, we saw that the iron paper clips were getting attracted towards the iron nail, isn't it? So, why do we use a iron nail? Why? We could have used some other things also, right? But every time we used iron nail, isn't it? Can't we make a magnet using only a wire carrying electric current without an iron nail? Like we know that whenever current is passing through a conductor or electrical wire, what happens? It shows magnetic properties. Then what's the need of using an iron nail? To know this, we have to do another activity, okay? And for that activity, we have to collect certain items. What are those? Flexible insulated wire, approximately about 100 centimeter. Then electrical cell, big chart paper, iron paper clips, iron nail and magnetic compasses. And after that, what we have to do? Roll the chart paper into a cylinder with a diameter roughly equal to the width of a pencil. Okay, like this we have to roll it and after that secure it with adhesive tape. We have to secure the cylinder. Then we will do what? Tightly wind about 50 turns of the insulated wire around the cylinder to form a cylindrical coil. Secure the wire with adhesive tape. Okay, then we will surround the electrical wire around the cylinder. Then we will place the two magnetic compasses what we have collected. Okay, place the compasses near the two ends of the cylindrical coil. Then we will connect the battery with it. Connect the two ends of the coil with the terminals of the cell and observe the magnetic compass. See, whenever we connect the two ends of the wire with the electrical cell, what we can see? That the compass needle, both the ends of the compass needle is showing deflection, isn't it? Now, do the needles of the compasses show any deflection? Yes, it shows, right? And disconnect the wire from the cell. Now we will disconnect it, and after disconnecting, it's going to its original position, right? The compass needles, they are going to its original position. Now insert an iron nail into the paper cylinder and repeat the activities. Now we will enter one iron nail and we will again connect the wire with the battery. Now see the deflection of the two ends. It is much greater than the previous one, isn't it? See, is there any difference in the deflection of the compass needle? Yes, this time the deflection was what? Greater than the previous one, isn't it? So, whenever we disconnect it, it goes to its original position, right? So, now Place some iron paper clips near the two ends of the nail and connect the cell. And the iron paper clips, they are getting attracted, right? Are the clips attracted to the ends of the nail? Yes. So, when electric current flows through a cylindrical coil, it behaves like a magnet and deflects the needle of a magnetic compass. But whenever we use an iron nail, when we use an iron nail, it's when it is inserted inside the coil, the magnetic effect becomes much stronger and the compass needle shows greater deflection, isn't it? See, compared to the first case, the deflection was greater in second case when we inserted the iron nail, isn't it? So, from this we can say that when the current is switched off, the cylindrical coil loses its magnetic effect, which we already know, right? A current carrying coil that behaves like a magnet is called as electromagnet. Very important line. So, a current carrying coil that behaves like a magnet is called an electromagnet. And for practical applications, most electromagnets use an iron core to make them stronger. Okay. See, in the second case, what was the effect? It was much stronger, much more stronger than the first one. Right. So, for practical applications, we use what? Most electromagnets use an iron core to make them stronger. So, note it down everyone. A current carrying coil that behaves as a magnet is called an electromagnet, and for practical applications, most electromagnets have an iron core to make them stronger. Clear everyone? Okay, so here comes our first question. Let's see. What is the main advantage of an electromagnet over a permanent magnet? Four options are there. Option A, it is always stronger than a permanent magnet. Option B, it can be turned on and off whenever required. Option C, it does not require any electricity. Or option D, it can attract non-magnetic materials like plastic. Which one will be the right answer? Your time is already started. So try to answer everyone. What is the main advantage of an electromagnet over a permanent magnet? Four options are there. Option A, it is always stronger than a permanent magnet. Option B, it can be turned on and off whenever required, like based on our need. Option C, it does not require any energy or electricity. Or option D, it can attract non-magnetic materials like plastics. Which one will be the right answer? Tell me. Very good. So many of you all have already given the right answer. And your time is almost up. Try to answer everyone, okay? And with that, your time is up. Let's see. Very good. So many of you have given the right answer. So our right answer will be option B. So based on our need, whenever we need, we can turn on or off the electromagnet, isn't it? Whenever we want to use it as a magnet, we will start the current flow, and whenever we don't need it anymore, we can just simply turn off the switch, isn't it? So by our own will or according to our own will, we can turn it on or off, okay, whenever we require it. Clear? So our option B will be right answer. Okay. So next, what are the other ways to change the strength of an electromagnet? Like as we saw this time that whenever we use an iron core, the strength increases. But is there any other ways by which we can increase the strength? Let's see. See what are we doing here? That we are increasing the number of coils. isn't it? So increasing the number of turns in the coil makes the electromagnet stronger. Then we are placing two batteries instead of one battery, isn't it? So then four batteries are used. See, look at the deflection of the iron compass needle. So the deflection is greater, much more greater than previous ones, right? So a single cell provides only a small amount of current to the, so the magnetic field produced is weak. As a result, the deflection of the compass needle is small. But whenever we are using the greater number of batteries or increasing the number of batteries, what we can see? A battery with more cells provides a larger current compared to a single cell. This produces a stronger magnetic field. So the compass needle shows greater deflection, isn't it? So compared to the first case, in the second case, what we observed that the compass needle, the deflection of the compass needle was much more greater, isn't it? So by this also we can increase the strength. Thus, the strength of an electromagnet can be changed by changing the amount of electric current flowing through the coil, the number of turns of the coil, or both, by doing both the cases. Okay. Now comes our next question. Let's see. Which of these actions will increase the strength of an electromagnet? Four options are there. Option A, removing the iron core. Option B, decreasing the number of turns of the coil, or using a plastic core instead of an iron core, or option D, increasing the current flowing through the wire. So your time starts now. Try to answer everyone. Okay. So which of these actions will increase the strength of an electromagnet? Four options are there. Option A, removing the iron core. Option B, decreasing the number of turns of the coil. Option C, using a plastic core instead of an iron core, or option D, increasing the current flowing through the wire. So try to answer everyone. Yes, very good. So many of you have already gotten the right answer. Rest of the students also try, okay? Wow, very good. So many of you have already answered the right answer. Very good. And with that, your time is up. Let's see. Very good, very good. So many of you have given the right answer. So our right answer is option D, increasing the current flowing through the wire. As we saw, instead of one battery, if we use more number of batteries, the amount of current flowing through the wire also increases, and by doing this, we can also increase the strength of the electromagnet, isn't it? So our right answer will be option D. Okay, increasing the current flowing through the wire. Okay, so does an electromagnet also have two poles like a bar magnet? To know this, let's see. Level the two ends of a coil as A and B. Okay. Place the magnetic compass near end A of the coil. And now connect the coil to the cell and observe the compass. See. Note which pole of the magnet compass is attracted towards end A. It is the red side, that means the north side of the magnet, north pole. Now, unlike poles attract each other, as we know, right? North pole attracts south pole, similarly south pole attracts north pole. So A means what? South pole, that is why it's attracting the north pole of the compass. Repeat the activity to find the polarity of end B as well. So we will place the compass near it and we will connect it to the battery. Now what we can see, that the opposite side or the south pole is getting attracted towards the B side, isn't it? So unlike poles attract each other. So that means what? That the B side of the wire is what? The north pole. So A was south pole and B was what? North pole. So do you find that the polarity of and B is opposite to that of and A? Yes, we found it, right. A side is what? South pole and B side is north pole. That means they are unlike poles. See, north side, it is attracting towards the south pole, and the south pole, it is attracting towards the north pole. So just like a bar magnet, an electromagnet also has two poles. One is north and another one is south. Clear everyone? Very good. So now reverse the direction of current by reversing the battery connections. So now we will change the direction of the battery and see what effect we can observe. What happens to the poles of the electromagnet? See, the north pole first and the opposite one is south pole. The current is flowing towards this direction in the first picture, and in the second picture it is going on the another direction. See, in the first picture it is on this side, then this side, up to this portion again. But in the second picture it is there, from there to again back to this side, isn't it? So this time the flow of the current, we have changed the direction of the flow of current, isn't it? So the poles of an electromagnet can be reversed by changing the direction of the current. Okay. So here comes our next question. Let's see. An electromagnet is connected to a battery and is attracting paper clips. If the direction of current through the electromagnet is reversed, what will happen? Four options are there. Option A, the paper clips will no longer be attracted. Option B, the north and south poles of the electromagnet will switch places. Option C, the electromagnet will become twice as strong. Or option D, the electromagnet will lose its magnetic effect. So your time is already started. Try to answer everyone, okay? An electromagnet is connected to a battery and is attracting paper clips. If the direction of current through the electromagnet is reversed, what will happen? Four options are there. Option A, the paper clips will no longer be attracted. Option B, the north and south poles of the electromagnet will switch places. Option C, the electromagnet will become twice as strong. Or option D, the electromagnet will lose its magnetic effect. Which one will be the right answer? Try to answer everyone. Very good. So many of you have already given the right answer. And your time is up. Let's see how many of you have given the right answer. Very good. So many of you have given the right answer. So our right answer will be what? Option B. As we saw earlier also, whenever we are changing the direction of the electrical flow, the poles of the magnet also change its direction, right? So our option B will be the correct answer. The north and south poles of the electromagnet will switch places. That means in this case the north pole will switch into south pole and south pole will switch into north pole. Okay, clear everyone? Okay, very good. So moving on to the next part. Are electromagnets used in real life for lifting objects? C. Lifting electromagnets are widely used in factories and scrapyards to move, lift and sort heavy metals objects efficiently. Okay, so where is it used? In factories or scrapyards to move, lift or sort heavy metal objects efficiently. See, like this, with the help of the big cranes. Okay, so these are powerful electromagnets attached to cranes. Like this, we can easily pull the objects made up of metals. The crane operator can control the magnet by switching the current on and off. And whenever he needs to drop the objects, he just simply turns off the switch and the electromagnetic effect, it disappears, isn't it? So when the current is switched on, the electromagnet attracts and lifts iron or steel objects. When the current is switched off, the magnetic field disappears and the objects are released. Okay, clear everyone? Okay. So moving on to the next part. Where else do we use electromagnets? Can you tell me where else we use this kind of electromagnets? See, here this kind of electrical bells. Whenever we click the switch, what happens? The bell starts to ring. Because why? Because the current is flowing through the circuit and it is producing an electromagnet. And by using that electromagnetic effect, we are easily able to bell the ring. And in electrical fans also, the one we use in our daily life. So here also, see, inside the fan, there is this, so many coils are present here, isn't it? So here second and third one is the sound box, which we usually use to listen music, isn't it? Here also. So our next question is here. Let's see what's the question is. A student makes an electromagnet by winding insulated copper wire around an iron nail and connecting it to a battery. However, the electromagnet does not attract any pins. Which of the following could be the reason? So a student, he makes an electromagnet by winding what? Winding an insulated copper wire with an what? Around an iron nail and connecting it to the battery. However, the electromagnet does not attract pins. Which of the following could be the reason? 4 options are there. Option A, the wire used is insulated. Option B, the battery is dead and no current is flowing. Option C, the iron nail is longer than usual. Or option D, the wire is wound closely around the nail. Which of the following could be the right answer? Tell me. Try to think about it just a little bit, okay? What could be the possible reason that the electromagnetic effects, it's not showing that? Okay, he made one electromagnet by winding insulated copper wire around an iron nail and connecting it to a battery. Okay, everything he did was almost correct, but still the electromagnet does not attract any pins. Which of the following could be the reason? What could be the possible reason? The wire used is insulated, that's why. Or option B, the battery is dead and no current is flowing. Or option C, the iron nail is longer than usual. Or is it option D, the wire is wound closely around the nail? Which one of the following could be the right answer? And your time is up. Let's see. Very good. So many of you have given the right answer. Very good. So our correct answer will be the option B. The battery is dead and no current is flowing, because his procedure was almost correct. It's just because the battery, it's dead and it's not able to pass or any kind of current flow. Okay, so that's why the electromagnet, it's not attracting any pins. Clear everyone? Okay. See, it's a bar magnet, isn't it? And the opposite side, this side, it's the north side, and this side is the south side. And the magnetic bar, it is freely able to move. So in which direction it will stop? Right, in north and south direction, isn't it? A freely suspended magnet always comes to rest along the north-south direction, isn't it? Like we saw in this case. The freely suspended magnet, it rested along the north-south direction. Why is this thing happening? Why always a bar magnet? It stops only a certain direction, only facing north or south. This is happening because the earth itself behaves like a giant magnet. Okay, because our earth, the planet which we live in, that earth itself behaves like a giant magnet. But why does the earth behave like a giant magnet? See, to know this thing we have to be clear about. Okay, so deep inside the earth, the movements of molten iron in the core creates electric currents which generate a magnetic field around the earth. So what's the case? That inside the earth's core there are molten iron. Okay, it's in the core of the earth, and it creates the electrical currents. Okay, and that's why due to the electrical currents, magnetic field is generated around the earth's surface, and that is why our earth itself works like a magnet. Clear? See, there are so many birds, they are flying. How they are able to know the direction? Many migratory birds, fish and animals use this magnetic field to navigate across continents and oceans. See, they have this ability to feel the magnetic field. Okay, so by using that magnetic field, many migratory birds, fish and animals use this magnetic field to navigate across continents and oceans. By this, they are able to know the directions. Okay, see, the radiations, these are coming towards the earth, but due to the earth's magnetic field, the earth's magnetic field also acts like a protective shield by blocking harmful particles coming from space and helps protect life on earth. Okay, so due to the presence of this magnetic field, the earth is able to protect us from various kinds of harmful particles. Okay, by simply blocking it. Now comes our next question. Let's see what the question is. What happens to the deflection of the compass needle if we increase the number of cells, thereby increasing the current in the circuit? Four options are there. Option A, the deflection decreases. Option B, the deflection remains the same. Or option C, the deflection increases. Or option D, the needle stops showing any deflection. Which one will be the right answer? Tell me. Your time is already started. Try to answer everyone. Okay, what happens to the deflection of the compass needle if we increase the number of cells, thereby increasing the current in the circuits? Four options are there. Option A, the deflection increases. Option B, the deflection remains the same. Option C, the deflection increases. Or option D, the needle stops showing any deflection. Try to answer everyone. Okay. Yes, very good. I can see so many of you have already given the right answer. Rest of the students, try to answer. Okay. What could be the reason? What could be the actual thing which is happening here? If we increase the number of batteries, by increasing the number of batteries, we mean to say that we are increasing the current, okay, flow of the current. And with that, your time is up. Let's see. Very good. So many of you have given the right answer. Very good. So our right answer will be option C, the deflection increases, isn't it? Very good. See, here there is one electrical coil and we are connecting it to a battery. So what is happening? The current started to flow, and for that, when electric current flows through a conductor, it produces a magnetic field around it. We all know this, right? Whenever the current is flowing through a conductor, it produces a what? It produces a magnetic field around it. And if we place a bar magnet, see what is happening to the light. It is glowing, isn't it? Whenever we are placing the magnetic bar inside the coil, the light, it turns on, right? So just as electricity can produce magnetism, a moving magnet can also produce electric current. Like this, whenever we are turning on the switch, the current is able to flow inside the current or electric wire, and the magnetic field, it is also generated, right? So this connection between electricity and magnetism forms the basis of many devices, from electric motors to power generators, by using this method. Okay, so here comes our next question. Let's see. Which of the following does not use an electromagnet to function? Four options are there. Option A, an electric bell. Option B, an electric fan. Option C, a loudspeaker. Or option D, an electric iron. So I have started the timer. Try to answer, everyone. Which of the following does not use an electromagnet to function? Try to remember the examples which we observed. Okay, which one was not listed among this? Is it an electrical bell, or an electrical fan, or a loudspeaker, or an electric iron? Which could be the right answer? Yes, very good. So many of you have already given the right answer. Very good. Your time is almost up. Try to answer, everyone. Okay. And with that, your time is up. Let's see. Very good. So many of you have given the right answer. So our right answer will be option D, an electric iron. Okay. So we observed electrical bell, electrical fan and loudspeaker. In all the cases, what we observed, that they were using electrical magnetic effect, isn't it? So our correct answer will be what? An electric iron. It does not use electromagnetic function. Okay, everyone. So I hope what we have studied today, you almost got every topic. So try, let's revise this, everything. Let's try to revise for a short period of time. So what we saw in our class today, that whenever a current is passing through a conductor, the electrical flow is generating a magnetic effect, isn't it? And by using that magnetic effect, we can easily able to attract various kinds of objects like iron paper clips. And after that, we saw how to increase the strength of those magnetic currents. By which manner? By increasing the number of coils, by increasing the current flow, or by increasing the what? By increasing the number of batteries. Okay, so by using all these methods, we can easily increase the strength of the magnetic fields. And after that, what we saw, by using this magnetic field, we can easily attract so many metal containing things like iron bars or objects made up of aluminium, isn't it? So by using these methods, many factories and scrapyards used to collect or sort out various kinds of objects, isn't it? So I hope all of you understood what we have learned today. That's it for today. We will be meeting you with another new topic in our next class. Till then, stay happy, stay healthy. Bye bye.